Ladies and gentlemen, hello and welcome back once again to Hot Technologies of 2013. My name is Eric Cavanaugh. I will be your moderator for today's event, which is featuring a reunion of two of the sharpest minds in the business, ladies and gentlemen. We're very pleased to have Dr. Robin Bloor and Philip Howard of Bloor Group and Bloor Research, respectively. We're going to be talking to Infobright. So let's go ahead and jump right in, ladies and gentlemen. There is a slide about yours truly and enough about me. This year is hot. Boy, oh boy. It's been hot for about the last 18 months or so, what's happening in our business. Obviously, you've all heard about big data. If you're in the industry, you've heard about it. If you're in the media, you've heard about it. If you work anywhere in the world, you might well have heard about big data because that's how hot the topic is. And when we talk about big data, usually we're talking about things like machine-generated data. There are other kinds. Of course, social media is hot data, or is big data, I should say. There are lots of different kinds of big data, but getting a handle on it, that is the big challenge, and that's what we're going to talk about today in the context of something called investigative analytics. So what is that exactly? So seeking previously unknown patterns in data, of course, extracting real-time insight. And timing is of the essence. Timing is everything, as they say. If you can detect a problem right before it's about to happen and stop it, that can save you a lot of money. It can save you headaches. You can make more money. You can keep customers happier. And that's the case all across any number of industries. So we'll also be talking about root cause analysis, because that's really where a lot of this machine-generated data can offer tremendous value by figuring out what exactly went wrong where. And we're going to get some analysis from our vendor and also from our analysts on the line today. And one of our attendees actually threw out an interesting description of what she calls root cause analysis, and I'm going to read it to you. I think it's very compelling. The cause is a variable which precedes the results and is correlated to them. Root cause is the combination of conditions that make this variable to appear more correctly to assume the value that makes the target results of interest. Very interesting stuff. So it's complex is the bottom line. Trying to get to the root cause of things, you need to watch out for the difference between causality and correlation and coincidence. For example, how do you get to the bottom of that? Well, we're going to find that out today, folks. So there are our speakers. Philip Howard calling in from the UK, Dr. Robin Bloor calling in from right here in the United States in Austin, Texas, and Don DeLoach calling in from Canada up in the Toronto area. We'll hear from first Philip, then Robin, and then Don. Then we'll have a nice round table, and we'll finish off with a discussion with our audience. So please don't be shy. Feel free to send your difficult questions to our guests, and we'll dig them up and use them in the Q&A. So with that, I'm going to hand it over to Philip Howard. Philip, I'm handing the keys of the WebEx to you right now. If you would, just click on that slide anywhere and use the down arrow on your keyboard, and the floor is yours.
Thank you, Eric. Yes, good afternoon, good evening, or even good morning, wherever you are. So I'm Philip Howard. I'm going to talk a bit about the Internet of Things and how you can use investigative analytics to exploit the information you get from the Internet of Things. So first of all, let's give some clarity to what we mean by the Internet of Things. In practice, people tend to think of it as any sort of sensor data, any sort of instrumented data that you can collect and use, and primarily for analysis purposes. So there are a whole lot of examples on here: smart grid, smart meters, intelligent medical devices. I heard recently about somebody, I've got down here golf courses, I heard somebody talking about actually having sensors in the greens on the golf courses so they could tell to detect how dry the surface was and therefore whether the green needed watering. There's an example I know of where people are tracking the icebergs moving around the place. So there are all sorts of different sorts of environments where you can collect data. So I think I have no, I want to go back to here. So for example, the average oil rig has 40,000 sensors on it. And historically, we've thrown that information away. I mean, it will raise an alert if something's happening right now, but nobody collects that data and analyzes it and looks to see if potentially that information could be used to predict faults. That if this part goes, then within a week, that part will go. So things like preventative maintenance. I've had different figures for this, and it may depend on the type of plane you're using. But I've seen figures of 9 terabytes and also 20 terabytes as the amount of information that's collected when an airplane is flying across the Atlantic, for example. That's a huge amount of data that we can use to analyze how do we improve fuel efficiency on planes, and so on and so forth. And so there are a huge number of things that we can automate to get information from. And the Internet of Things is the way that you can connect these different sensors and instruments to analytic processes and do it all automatically. I would say one caveat. Although we call it the Internet of Things, you don't absolutely have to use the Internet. You could, if your plane lands at Heathrow or Dallas or wherever it happens to be, put that data onto a USB stick or a portable disk drive and take it away physically and plug it in somewhere to do that analysis. And that actually might be safer. If you think about the potential of having a plane flying across the United States, which is collecting sensor data online, as it were, and feeding that into the Internet so it can be analyzed in real time, then you are open to hacking. And I've heard recently about an example where somebody, I think this was actually a demonstration event, that they hacked a car. And the hacker took control of the car, it was on a racetrack or whatever, and it took control of the engine control, drove the speed up to 140 miles an hour. Of course, he couldn't see where he was going, he wasn't physically there, he wasn't steering it, but he drove it, the speed up to that extent. And the way he got into the system was he hacked into the tire pressure sensor. And because that was connected to the main computer system, he was able to get to control the car. Now, if you imagine a plane which has fly-by-wire and autopilots and things like that, it might be very dangerous to allow people actually to have that on the Internet where it can be hacked. So, although we talk about this as the Internet of Things, it may not be sensible in all cases to actually use the Internet for those communications. Anyway, that's sort of an aside, but so the Internet of Things is to a certain extent a misnomer. That was the point I wanted to make. However, the truth is that everything nowadays is being instrumented in one way or another. So, investigative analytics. That's what we take that information and what do we want to find out? We want to find out what happened. We want to find out why it happened. And in particular, we want to find out if it's a part of a pattern that suggests that that event might happen again if those precursor activities, root causes if you like, or perhaps not root causes, but causes, something goes wrong that leads to a cascade of effects. And then we want, from a business point of view, once we understand that there is a pattern here, how are we going to react to that pattern? Now, is that a pattern that we can leverage for business purposes because that suggests that that would help us to upsell or cross-sell to a customer, or conversely to do things like preventative maintenance, or if we're in telco to analyze our network to see where it might be best to put a new mobile phone mast. So there are a variety of different reasons that we might use that for. So here are some example use cases. So if we start at the top left, we've got this smart home, if you like, smart metering, the ability for, you would like to be able to, for example, to tell your house that you are half an hour away from coming home could you please turn on the air conditioning or the heating if it's in the winter, so that the house is at the right temperature for you when you get home, but you haven't wasted time, you haven't wasted electricity or power during the day while you're away. And then, of course, you've got the utility providers who've got smart meters who want to have that information for billing purposes, but also want to be able to plan capacity. When do they need to scale up the production of energy, scale it down, and so on and so forth. I mentioned planes already. As I said, there are potential issues with planes if they are online because of hacking, but still there is an awful lot of information you can collect and analyze about the performance of aircraft. And we're living in a greener, well, hopefully a greener and greener world. You want to be able to, what's the best way to most efficiently make use of fuel and preventative maintenance as well. And the same applies on oil rigs. That's you want to be able to. We know what happens when things aren't properly maintained on oil rigs. You get explosions, you get oil leaks, you get all sorts of nasty things happening. If you can prevent that happening because you have established a pattern of what happens with the components on board, then you can help to prevent that. At the bottom here, I've mentioned telco being able to monitor calls. We know that one of the major causes of churn in the telecoms industry is people having dropped calls. So it's really important for the telcos to know that. But it's also important to understand how much traffic is going through so that they can plan future enhancements to the network. Then we've got things like mobile payments and automated teller machines. I mean, right now, automated teller machines don't collect information that's analyzed, but you could, the banks could analyze that information to see which teller machines are used most frequently and who buy, and therefore they could use that information to optimize their network to say, well, actually, we don't need this ATM here. We can remove that. That will reduce our costs here, but it would be useful to put one in over there because that will improve our service to customers and so on and so forth. And then the final example I've got here is from the IBM's X-Force survey for 2012, which shows hacking events during 2012. And if you've seen the 2011 diagram, which I have, this is much busier. So every year there seems to be more hacking attempts and so forth. And all the when somebody tries to hack your network, the way that you try to counter that is by collecting data from things like your routers and your application servers and your other bits of your hardware, log data, vulnerability information, so on and so forth, to analyze that information firstly in real time to try and identify what type of attack you're under and therefore what you should do to ameliorate that attack. And also there's a subsequent analytic capability to start to improve your ability to identify those sorts of attacks. So one common theme here is there's often two parts to investigative analytics. That there's often a real-time part or a near real-time part. Collecting the information, what do we do about it right now? Maybe this is an alert that we need to act on right now. And then there's a subsequent part, which is analytics for the future. When, where should we build more network capacity for a telco? Where should we, ramp up the power output from our power plants? Those sorts of things. So there's often that sort of two-stage process. So what sort of requirements do you need to support this sort of investigative analytics? Well, first of all, you've got, let's assume you're putting this into some sort of data warehouse or data mart or some sort of analytic environment. So first of all, it needs to scale. The volumes of data that we're talking about can get very large very quickly. I mentioned that, a single air flight across the Atlantic we're certainly talking in terms of tens of terabytes. And when you talk about all the flights every day that a single airline has got, you're very rapidly into hundreds of terabytes. And if you're talking about a worldwide network for a large airline, you're talking about very, very large quantities of data altogether. So you need platforms that can scale. Secondly, you need as much automation as possible. You really don't want to worry about database administrators who have to decide where's the best place to put an index, or how do I create a materialized view, or all of those sorts of administrative issues that, at least in the past, used to be frequent in database environments. Thirdly, of course, you need high performance. In real-time environments for alerts and queries, you need very rapid, real-time performance, but you may also need, but you're scanning a lot of data. You can't afford to be still analyzing the current data if you're, while you're still, while you're loading today's data. You have to finish processing today's data before, before you. Sorry, let me start that again. You need to be able to, the performance and the loading, in fact, the loading itself is a performance issue. You need to be able to load the data fast enough and process it fast enough. The next thing is that increasingly business users want self-service capabilities. They don't want to have to rely on going to the IT department to say, what is this, build me this query, because that will take them weeks or months. They want to be able to get at it and do it for themselves. And finally, you need flexibility. It's not good enough to have a fixed set of query environments. One of the things that always bugs me about some of the data warehousing vendors that talk about partitioning the data. Partitioning the data is fine if you know what queries you're going to ask, because you partition it according to how you're going to group the data together. If you don't know how you're going to query the data, which is frequently the case in this sort of environments, then you don't want to be constrained by things like partitioning or, for that matter, indexes or whatever. You need a flexible environment which allows you to ask any question that you need to ask based on the information that you've got, without regard to what sort of data that is or where it is. So that's my brief overview of the Internet of Things and Investigative Analytics.
Okay, good. Let me go ahead and hand it over to Robin Bloor. And Robin, go ahead and just click anywhere on that slide and use the down arrow. And the floor is yours. Then we'll have Don, and then the roundtable and the Q&A. So folks, send us your hard questions. They're ready for them. Go ahead, Robin.
Okay. Right. Seeing as there's two analysts on this, I saw Philip's presentation prior to him seeing mine. So I've tried to just do some counterpoint ideas in terms of what is it we're looking at here. We start with the idea, I guess, of intelligent things. It's fairly clear from what's happening that we're going towards intelligent things, but there's a question as to what that means, particularly what it means in terms of IT. And the way that I've come to think of it is that this is really all about state. People, objects, systems, system components, pretty much everything can be viewed as actually always being in a particular state and moving from one state to another state to another state. And every time there's a state change, there's data that can be gathered about the state. So we have things like RFID tags and sensors. We have various log files produced that are effectively reflecting the state at a given point in time. Even tweets are actually reflecting in some means, in some way or other, reflecting the state of an individual at the time that they actually tweet the information. all of this is what I like to think of as the new BI data. There's the old BI data, which I'll talk about in a minute, but this is the new BI data, and it has certain characteristics. But the thing is that things can report state, and when something reports its state, what in effect, or the way that I think about it, is those snippets of data are actually reports of events. Even if you get a situation, for instance, where you've got a sensor embedded in an oil pipeline that is giving you the rate of flow every second or something, you know, it may be reporting the same rate of flow 1 second ago as it reports now, but what you actually have is a snapshot event of this particular part of this particular pipeline at this particular point in time. And when, of course, the rate of flow changes or the temperature changes, then you have an event that possibly has significance. And the thing that I wanted to contrast was the difference between a transactional world, which is the world of IT that we all grew up in, and the event-based world. It's not like the transactional world has gone away. In fact, we've done reasonably well in terms of being able to automate a vast number of transactions across the planet, and that's still going on. It's not like the job is completed absolutely, but most of the technology to do that is reasonably well known, is reasonably well behaved, and performs reasonably well. So if we contrast transactional environments with event-based environments, I can go through this one by one, but a transaction normally corresponds to a system change. You know, an order has been placed, or an invoice has been raised, or goods have been received. And it's a change in the system rather than the change in the smallest component of a system. So I kind of think of that as a molecule of information. Whereas an event, really you're talking about an atom of information. It's one piece of information that corresponds to a state change. Transactional activity is process heavy and data light. In other words, an awful lot of, let's say, computer instructions are executed in order to deal with the data that's being handled. And the actual data that's being handled doesn't, in terms of its ratio to process, isn't particularly high. Whereas with events, it's process light and data heavy. In other words, there isn't much that's done in order to process an event. It might do nothing more than record it and pass it on. But in terms of the ratio to the amount of instructions to data, it's actually data heavy. And this obviously manifests itself in the term of big data. But the interesting thing about a lot of this big data is that machine-generated data is often really quite simple in the sense it's not complicated data. You don't analyze it as being consisting of 4 or 5 linked entities. It consists pretty much most of the time of one entity alone, and often not many data items. So it's actually fairly simple data, but there's a lot of it. When you analyze on the transactional side, when you do an analysis, what we call BI, on transactional systems, the BI happens downstream. It's nearly all looking backwards, or at best it's kind of oversight that's manifested through some kind of dashboard that shows you the state perhaps a few minutes ago. Actually, you know, you could even get it very close to real time, but it's showing you the past. With events, events are precursors to things happening. An event itself might trigger something, or a chain of events might indicate a trend towards something, kind of like what Philip's talking about, you know, that maybe some preventive maintenance needs to be done because we see a particular trend in the data as regards the behavior of a given valve in a, I don't know, on an oil rig or something. The analysis happens pre-transaction, so you're suddenly put in a situation where you may need to be analyzing a very large amount of data, but having analyzed it and realized that something significant is happening, we now have to act very quickly. So this is what I call the new BI. It's a different kind of BI. And one of the things is that the latency demands are extremely tight. You know, it's like if it takes you 10 minutes to actually assemble the data and produce an alert that something is about to fail in 5 minutes, then you're too late. You know, and you have that situation. You really don't have that kind of situation with BI in the traditional sense. Transactions flow as part of a business process, but you know, an event can actually trigger a business process, which might be, you know, anything from, you know, shutting a pipeline down or sending a maintenance engineer out, or pretty much anything in actual fact, because we're talking about gathering data around given situations and trying to respond to them before anything unexpected or unwanted happens. Transactional systems have to be fast, but they're normally good if they can respond at kind of human latency within 1/10 of a second, certainly within a second for most systems, and even other systems, you know, worse than that, and it won't do any damage to anything. But event-based stuff has to be extremely fast. Now, one of the things that isn't completely obvious, but I think is actually going to happen, what we've witnessed happening now is people instrumenting existing environments. So maybe people instrument a house in a way it wasn't instrumented before. Maybe they put temperature sensors in every room. Maybe they put them at the top of the room and the bottom of the room and under the windows and so on and so forth. Maybe you can do that. But what you're actually doing in that situation, and in every situation that we can conceive of right now, is you're instrumenting something that already exists. But if you had the kind of feedback that good instrumentation can create, it's very likely that you wouldn't design things in the way that you design them right now. You would probably start making changes in the design. So I think that this world that we've entered into, this world of events, actually has two steps to it. And the first step is instrument anything you can that will give us reasonable data in order for us to be able to do things more effectively or more swiftly, and so on and so forth. But the second part is, let's start designing the things that we deploy in this world in such a way that they're built to be instrumented. And I think that this is going to have a dramatic effect over time, because some of this is big engineering, but it'll have a dramatic effect on the world. For instance, it's the case that let's say the various sleuth systems that were built in the various American cities in order to siphon off water if there's a downpour, they were never designed knowing anything about the weather. They were designed just basically out of experience and people's gut feel for what's going on. Well, once you actually realize that you can have really good instrumented systems like those sleuth systems and series systems, you may actually start rebuilding them, or you may start augmenting them in such a way that you can actually make them far more functional than they were before. And those things are, if you like, they're there to deal with situations that have become extreme, you know, when 10 inches of rain falls out of the sky. Well, most of those systems break down under those circumstances. But you could possibly design them to have a much better tolerance for extreme situations. And that's, I think, what we're going to. So you go from the point of being able to analyze causes because you've instrumented many parts of a system that was previously instrumented, to being able to analyze situations because you designed stuff to deal with the environments that you knew about from your analysis of the past. Different world, I think. What I wanted to do is I present this fairly frequently, but I think it's worth doing, going through this again, because one of the things that's being demanded in the event-driven world is actually real-time reporting on things. And when you've actually got, you know, many terabytes of data, even up to petabytes of data, being able to deal with that and to get extremely fast response involves the management of data flow from end to end, for one thing. But the other thing that it involves is being extremely fast where you need to be fast. And that, I think, is the point. what I actually show here, in the color bands across indicate different latencies. The vertical scale is actually a logarithmic scale, so if you drew it as a regular scale, it would go through the roof and up by about a mile. But these curves that I've drawn that are labeled 1960, 1970, 1980, 1990, 2000, 2010, these kind of indicates what was possible. It's conceptual. I've put workload size and complexity along the horizontal axis, but there's no absolute measure of that. You know, if you've got a lot of data but you don't have to do much to it, then the workload isn't as big as if you have a lot of data and you need to run various complex analyses on it, and so on and so forth. If you've got lots of short, sharp transactions, then you know, those could be handled in the 1980s and the 1990s, and to get really good user performance for those things. But business intelligence has always, you know, until fairly recently, has started to become batch. And what's actually being demanded of the world, and luckily we've got, you know, a whole number of things coming together. Like, for instance, we've got the advent of the cloud, so the possibility of deploying very large amounts of hardware very, very swiftly. And at the same time, we've had, you know, we used to have clusters of systems. That was as big as it got, except for very specialist MPP systems. But now we've got grids everywhere. So now a lot of things are possible in terms of speed. And these white arrows that indicate, you know, that are going down towards more and more real time is the direction, in my opinion, of the way that business intelligence is going, and certainly it's being accelerated when we look at what I would call the new BI. And that's, I think, the situation that we're in, and we're starting to see a whole series of technologies coming to market that can actually do some of this, can actually get you, you know, that can examine a terabyte of data and get you answers within seconds that you can actually act upon, and you can maybe intervene in a business process. There's three latencies that are worth mentioning. This is especially true of analytics. There's two kinds of analytics in a way. One is the analytics by the guy that's investigating data to develop, to generate insight. And then there's the analytics that is automatically employed later on once you've found something that's particularly valued and implement it. But there are three latencies to worry about. One is the time to analyze, or what I call time to develop, but nowadays the developer happens to be a data scientist. There's the time to deploy, which could previously have taken, you know, if you ended up needing like 10 servers or something to implement something, ordering that and sticking it in the data center could take a very long time, weeks, months, you know. But the time to deploy in the cloud nowadays, certainly for a number of applications, is actually very swift and can be measured in minutes. And then you've got the user experience. You know, even if you bring down the time to develop and the time to deploy, then the user experience is, it actually has to be, you know, the user might be a piece of software. The user experience, the performance at that particular point has to be extreme. So, you know, boiling all of this down, or from the point of view of the analytical side of it, this is all about time to insight, and then as long as that can be followed by fairly instant action. But this is against big data, and mostly it's against big data but fairly simple data. In other words, we got volume, but we don't have extreme variety, particularly in the machine-generated area. Anyway, I think that's enough from me. I can hand on to Don. I'm sure he'll put me and Phil right on the various things you said that might be wrong.
That's it, Don. So I'm handing it over to you right now. Just use the down arrow on your keyboard after clicking on the slide.
Okie doke. Okay, thanks. Let me just start by saying it was observed early on when we were talking ahead of this that, you know, for Infobright, machine-generated data is everything. So the Internet of Things is kind of right in our wheelhouse. And it's definitely something that we're spending sort of all day, every day, focused on, and it's really exciting. The thing that I try to always go above and beyond to state, though, is that there's a lot of clever technologies in the market, and we don't, you know, I have unbelievably strong respect for a lot of the technologies that are out there. I'm not somebody that believes that you know, if somebody buys our product, it makes them smart, and if they buy anything else, it makes them stupid. And in fact, what I spend more time and emphasis on is just trying to understand where we fit and why in the context of other things. So Infobright is a column-based store, but we're not focused on being a general enterprise data warehouse. We just really focus on machine-generated data, and as such, like I say, this topic is extremely important to us. So as we look at the types of data we deal with, that's generally things like call data records, sensor data, IT logs, web logs, network events, data that is auto-generated, and it typically is highly structured. So the discussion was focusing a great deal on, you know, what are the requirements from a practical standpoint in terms of investigative analytics. And by investigative, we mean, you know, fundamentally that the query that you're asking is informed primarily by the result of the prior query. So you're digging and iterating in order to get to an endpoint. And as it relates to the Internet of Things and machine-generated data, you're parsing through a lot of data to try to understand where are there patterns, where are there issues, and why are there issues. So ad hoc performance is extremely important. It's probably the anchor concept to all of the investigative analytics work. Load speeds we see being more and more an issue. I'll talk a little bit about a couple of different examples where the load speeds on the networks were of particular concern in terms of being able to keep up with the scale issues in load speeds. Compression gets more and more important as you're storing very, very large amounts of machine-generated data. The ability to store that in a reasonable footprint has all kinds of implications. It has cost implications. It has retention implications. So if I want to store, you know, 30 days versus 7 days worth of data, and there's certainly instances where there's value to doing that, then all of a sudden I have hardware issues as well to deal with. And all of these are, you know, different cuts at scalability, which are very important in terms of how do I instantiate my environment, how do I maintain my environment, but even more so, one of the biggest costs that we've seen that is subtle in some ways, but almost overriding in others, is actually the cost of the people associated with maintaining these environments. You know, as it was discussed before, you know, the idea of investigative analytics is you don't really know what you're going to ask. And if you don't know what you're going to ask, you can't really set up indexes and partitions and do the type of things that you can do in a pre-planned world. And the ability to create an environment that's suitable for investigative analytics is also one that requires that you figure out a way to do that without having to have, you know, database administrator after database administrator deployed in order to keep the environment performing. And all of this has to be done in an affordable way. So these are some particularly interesting challenges. And again, it's something that we care about so much because we actually take shortcuts in terms of what we do. We make assumptions about the data structure, and as a result, we're able to do some things that give us some unique capabilities, but fundamentally there are a lot of things that other really elegant solutions out there can do that Infobright wouldn't do just because we wouldn't be architected to hit a broader range of use cases. So as we look at the emerging data analytics stack, you know, all day, every day we hear people talking about Hadoop and NoSQL, and there are certainly all kinds of good reasons for that. And we believe that, you know, it's not going away, that it's definitely a part of the stack that is being incorporated more and more. There are some fabulous aspects to some of these technologies, whether it's, Hadoop with HDFS underneath or Cassandra, or whether it's, MongoDB. There's all kinds of, really elegant offerings out there. But again, they have different characteristics. One of the characteristics that does not seem to be as advantageous for these type of technologies is the ability to do macroscopic dicing and slicing and investigative analytics of this data. So, for example, in the ad tech space, we have, gosh, we probably have over 100 customers in the ad tech space, of which I'd say well over half of them use Infobright in conjunction with Hadoop in order to move the data that they care about into Infobright for dicing and slicing. And since we're talking about Internet of Things, I'm not really going to spend a lot of time talking about what we're doing in the ad tech space, but fundamentally the technologies are very symbiotic in nature. The key is to enable the analysis, to enable both the operational, the investigative, and predictive analytics into a usable environment. I think somebody asked the question about the connection between investigative and predictive analytics. You know, I think a lot about, you know, my prior days in the trading world where, you know, like proprietary trading shops would be trying to develop algorithms that would then be put in place on a predictive basis to do auto trading. And the idea would be you parse through and you mine the data and you try to understand enough about that data to determine what type of predictive patterns you can employ. And I think the same will be true on a very, very broad basis on the Internet of Things. So to the extent that the analytics stack can be integrated, that becomes more and more powerful. You know, today, you know, in full disclosure, I think, you know, I think we at Infobright focus a lot on the integration between the operational side and the investigative side. We certainly have customers that add the predictive layer in some in very, very elegant fashion, but I believe that that is a foreshadowing what we'll see more and more. So just to say a little bit about what we do, and then I'm going to go to specific use cases. The thing that we do is we make assumptions about the data. So when we absorb the data, we invert the file structure like all of the column stores do. But then we employ a body of work called rough set mathematics applied to granular computing concepts, which I won't really go into here. But fundamentally, the idea is we instantiate this metadata layer that not only contains the physical pointers to the data on disk, but it contains information about the data. And what this generates is an ability to get at the data as if everything were indexed. So it's tantamount to indexing everything, but you're not actually touching the data at all. So there's no database administration required to establish or maintain the environment. Because of the way we go about this, we get unbelievably tight compression. So generally anywhere from about 10 to 40 to 1 compression. We get exceptionally high load speeds. So we're able to build and maintain this environment in a very, very low touch fashion. So it becomes extremely useful if I'm deploying use cases that are designed to store and analyze machine-generated data. One of the best examples of this, and what I'm going to really focus on, are areas in the telco space around OSS. And the reason, although I'll mention a couple of others, the reason that's important is if you look at the characteristics required by the telco space in OSS applications in today's world with greater and greater scale, and then you apply that logic or you apply that set of characteristics to what logically will be the demands in deploying systems to support the Internet of Things, there is a very, very logical progression. You know, I had a conversation with a venture capitalist a few weeks ago talking about Facebook, and you know, they had been involved with the financing of Facebook, and they said, you know, if Mark Zuckerberg had walked in the office and said, we're going to show you a platform that will connect 1 billion people, it would be a 15-minute conversation. Nobody's going to sit down and say, okay, let's look at something that is designed to be the end-all, be-all. But what Facebook did was to look at, well, how do I connect college campuses, and what is it about that connection that then gets to the next phase and then the next phase beyond that ultimately evolves into something, you know, huge. And when I look at the Internet of Things, and when I think about the Internet of Things and the characteristics that are a requirement for deploying these type of systems in the future, some of the characteristics that will be obvious are very, very similar to what we are currently seeing in the telco OSS world. So I'm going to speak to that here in just a second. So fundamentally, the capabilities are really around the ability to query that data in an ad hoc fashion, but in an extremely efficient deployment capability. Low hardware, very, very low touch, and then collapse the time to value in terms of getting at that data. And it's not so much big data as it is smart data. How do I understand and act on the information I'm receiving that may be coming from human beings, but more often than not, or more and more often, will be coming from things. So if you think about it graphically, and when I think about this is actually a representation of work we've done with certain telco solutions. So in today's world, they have data that's deployed across many databases, multiple sites, large volumes of data. And as the scale issues mount, as I have more data within a certain time frame, more call data records within a certain time frame, I keep having to index the data to keep the performance where it needs to be, and that grows the footprint, and that grows the hardware. And that requires more and more database administrators just to deliver the application. The goal is to shrink the hardware, remove the database administrators, shrink the data footprint, although increasing the retention and increasing the actual amount of addressable data in order to service the same application. And we have a number of examples where we've done this, and I'm going to just speak to a few. By the way, so everybody that I will speak about is our customers that have allowed us to use their name publicly. So I'm not going to say anything that you couldn't actually investigate and find on either our website or out on the web. In some cases, there's some nice YouTube videos that speak to this stuff as well, JDSU being one of them. I find the JDSU story is always more compelling when Chuck Gruber from JDSU tells it than I do, but it's a great representation of what I'm talking about. So in their case, they had a system that was deployed that used a traditional relational database that everybody would know. And it was basically designed to troubleshoot networks. It's called Session Trace. And the issue they were having was that 7 days of call data records 2 years ago was far more dense than 7 days of call data records 5 years ago. And in order to keep the application running, their users, the large mobile network operators, of which they have about, they have a considerable number of mobile network operators that are using this application, were struggling to keep up because they kept having to index the database, and that required people, that required hardware, and that's not desirable. So they came to JDSU and said, we really want to improve we want you to improve the operation of this offering. And so the goal was to do a few things. The goal was to reduce the disk footprint while increasing the load speeds, while increasing the retention period, while stripping out the administrative overhead. And that's, doing any one or two of those simultaneously is kind of a tough call, but to do it across that type of range really had them looking for disruptive technology. And again, our whole approach is really to make assumptions about the data where we can effectively take shortcuts. And again, it makes us more narrowly scoped, but where it's in our wheelhouse, we have some unique advantages. So long story short, this has long since been deployed. They were able to increase their retention period over threefold, while seeing a simultaneous 5x reduction in the storage requirement. They were also able to dramatically increase the ingestion rates, and theoretically that can scale, way beyond a terabyte an hour. And we're also able to federate the load. But more than anything, we stripped away the DBA requirements, so that made it much more palatable for their users. And in fact, the feedback we received, from their users has been, nothing short of fantastic. And that actually the thing that kind of surprised us is that amid all of that, we actually also were able to deliver better performance, so all at a lower cost. So the characteristics that were demonstrated here we've seen over and over, but we believe that they're very consistent with the challenges people have and the desired outcomes people have when addressing these scale issues. Another example would be Mavenir. Mavenir is a company that deals in the mobile convergence space. Their big challenge was really around load speeds, where some of their customers had requirements where they had to handle very, very, very high load speeds because they had to capture, for example, in some countries you have to capture every SMS message you process. And in the case of places like Vietnam, on the Chinese New Year, they get spikes, sometimes 10x what they normally see, and therefore load speeds were an issue. In their case, they were able to increase their load speeds as well as increase the retention and therefore their reporting. So again, many of the same characteristics. Another example, and I'm trying to go at a pretty quick rate here, another example would be Polystar. Polystar is an OSS supplier in Sweden. And in their case, they were able to increase, well, they were having scale issues in terms of their queries. And they just weren't able to deliver the type of query response that they needed because the volume that was on the network was growing higher and higher and higher. They were able to increase their query performance dramatically by changing their technology that was underlying the system, and actually spoke to not only to the operational people, but beyond that, customer service, marketing, and other users of the system that wanted to get their hands on this smart data to help them reduce churn, increase upsells, et cetera. So it goes way beyond just the network monitoring, all the way in through to customer insight, and it's been a fabulous success. One other recent addition that I'll talk about is OPower, and in OPower's case, they were a fast-growing company in the smart grid technology space, and they wanted to have much faster, much more flexible reporting against a vast amount of data that they were collecting, and felt that their existing technology for doing that really needed to be better suited for this specific use case, and that has gone in. It's been a great illustration of what we think we can deliver for other Internet of Things type applications, and that has been a nice success. So again, those are just 4 quick illustrations. We have customers in a wide variety of spaces, but mostly we see a concentration in the ad tech space where there's online analytics, mobile analytics, online gaming. We're doing a lot of financial services, especially in the area of log capture and message management. But a really large portion of what we're doing is focused on telecommunications and the mobile network operators, which we see as the leading indicators or really out in front of the Internet of Things. So if you think about not only the mobile network operators, but the companies that are servicing the mobile network operators, they have everything to gain by being at the forefront of enabling the Internet of Things. So smart grids, smart vehicles, smart cities, mobile health. Many of the examples we've already talked about, we believe will be first and foremost ushered in by the companies servicing the mobile network operators that really combine 2 key things. It's the combination of advanced communication technology and advanced sensor technology. Smart energy delivery for electric power, there are 23 different specific sensor technologies working together that collectively allow power generation producers to vastly decrease the amount of money it takes to generate and deliver power. And we think that that's a really good indication of the type of data that's going to be put out and the type of data that will need to be consumed and analyzed as the Internet of Things becomes a reality. Fundamentally, at the end of the day, we think that the combination of a very low-touch environment with high capacity and high density is going to be what will be required for these types of systems. And we think that the sort of the permutations of this are endless. that's not to say that it's the end-all, be-all. There's all kinds of issues. I think it was Robin that pointed out the whole idea of security. What will security be for smart grids or for connected cities? What will connected cities look like? There's all kinds of questions that people are beginning to think about now that they are starting to think more and more about the Internet of Things, and we think it's great. We think the Internet of Things will change the world. I have to give kudos to IBM. I think that, as far as other companies go, IBM has done a really nice job of embracing the Internet of Things with the Smarter Planet initiative. If you look around, all kinds of other companies are going forward. HP, Cisco. There's a widespread recognition that this is a technology that will really change the world as we know it, and it's really cool to be a part of it. So I know I kind of jammed a lot in a very short time period, but I really appreciate the opportunity, and I wish everybody all the success.
Yeah, sure. So let me dive into some good questions here. You mentioned smart vehicles, and of course we're talking about real time, and it's the sort of really real time kind of environment that we're discussing. As Robin was suggesting, if something is going to break in 10 seconds and you need to know about it in time, if you find out in 20 seconds, that's too late, right? So you mentioned smart vehicles, and I'm wondering, could you implement some of this technology in vehicles, whether it's a car or a plane or some other kind of heavily instrumented device, such that you could get early warning signs of, hey, engine B is going to go out in probably 2 minutes. Let's go ahead and divert this flight right now to a nearby airport. Is that the kind of thing you could enable? And if so, what would that architecture look like?
Sure. Well, that would not be what something like a historical repository would do on its own. So this is where architecture is everything. So there are technologies like complex event processing that do executions, do the execution side of things that are required for things that are sub-millisecond. Like the technology involved with smart vehicles involves sensors that will sense the car in front of you or the kid jumping out from the curb or whatever and respond instantaneously. That is not a back-end database function. That is an execution system function. The interesting thing, and I think what you're going to see more and more, is a very, very elegant link between the execution side of the architecture and the data repository side of the architecture, so that the signatures and the patterns that are derived from the historical data can enhance the execution systems more and more.
Right.
And actually with less and less latency. So the idea that I'm going to have a signature that gets adjusted in a 2-minute time frame versus one that takes me 24 hours to adjust is very real.
Yeah, so in other words, you would use some of the technology that you're talking about here to bolster the kinds of CEP systems in some of these instrumented devices as a way of improving their ability to detect patterns. In other words, you would see upon historical analysis that whenever this one gasket blows, there's a 50% chance that this other part is then going to fail within 5 to 10 minutes. So now let's incorporate that kind of pattern into the event stream analytics that we use in the actual device, right?
Absolutely. Absolutely.
Yeah.
There's IT log management systems out there now that are beginning to employ this type of technology. So if I have 240 different systems that are deployed on a global basis, and I see an issue with one system, and I know I have 239 others that look like it, we already have customers that are using us for doing that type of analysis, so that they can then make, take preventative action when they know something else is likely to happen.
Mm-hmm. Sure, and obviously a lot of this stuff has been going around for a while. In other words, I know in a lot of industries like avionics, for example, they've been doing this kind of predictive analytics, but what you're talking about is a very compelling enabling technology to feed those kinds of systems with the kinds of patterns that you can detect upon historical analysis, right?
I think so. I think with the Internet of Things, the range of problems being solved and the power of solving those problems is just going to be mind-blowing. I mean, there's so many opportunities for doing this once the systems are deployed where you're collecting that data and have the ability to analyze and act on that data.
Right, and you primarily pull your data from log files. Is that correct? I mean, I know you can pull from other types of systems, but primarily you're accessing log files from any number of operational systems, right?
That's sort of true. In many cases that's true, but it certainly isn't restricted in any way to log files. And
okay.
You know, we have customers that are dumping, for example, sensor data from doing satellite testing would be one example where it's very similar to a log file, but you know, it's not exactly. Trade data warehouse would be another example.
Oh, okay, good. Yeah, there was a question basically asking, it's a question I've heard before in other contexts, asking about, you know, how do you address the problem of collecting very large amounts of data in real time without impacting the performance of some kind of system in question?
Yeah, well, there's a number of ways you can do that. In our case, one of the things that we'll do is federate the load, where we'll actually ingest the data at distributed sites. Actually, ideally, you want to ingest it close to the site where you're loading the data, and then compress it at that site to where not only are you not impacting the main processing environment, but you're also really reducing the network traffic by compressing the data before you move it across the network. But again, you know, there's all kinds of different topologies that are used, and it all depends on the specific use case where the data is being generated and how it needs to be consumed.
Right, and I know a key part of your technology, and I can't remember the name of it, but there's a clever name you came up with it. They are little data packs or intelligence packs, basically, where in every chunk of data that you pull, as you kind of talked about this, you do some immediate analysis of it, and you store in a small packet of information a lot of data about various patterns, like, you know, high, low, median, all that kind of stuff. Can you talk about what you call those things and how they work?
Yeah, it's fundamentally our knowledge grid architecture. The metadata layer that we build is called the knowledge grid. It stores information about the data as well as the physical pointers to the data on disk. And when I say information about the data, so when we invert the file structure and absorb a column, you know, there may be 500 million records in a given table, but we will take each column and we'll break it into what we call data packs, or 64,000, a default value is 64K, so 64,000 values per pack. And then we'll collect information about that pack, min, max, standard deviation, sum of the nulls, stuff like that. The idea is to store the maximum amount of information in the minimal amount of space to resolve as many of your queries as possible, as quick as possible. There are some other nuances to this that are actually fairly unique in terms of your ability to run a query that returns a range and not an exact answer, but it's always going to be a sub-second query, even if it's a complex query over 40 terabytes of data. That's another hour-long discussion. But fundamentally, the message here is that this is an approach that, again, it employs a body of work called rough set mathematics applied to granular computing, and it gives us the ability to really do well in storing and analyzing machine-generated data. But it makes some assumptions, and the assumptions are that you're using limited number of tables with very large record counts. But once you write the record, you seldom, if ever, update it. And most general database architectures, again, some that I think are really great architectures, are designed to be more robust in their ability to address data that's quickly changing, where you're updating on an ad hoc basis, data in the records. That doesn't describe machine-generated data. That describes a lot of corporate, enterprise data warehouse type environments. But if you have limited number of tables, very, very limited update rates on an ad hoc basis, but huge amounts of records, that describes machine-generated data. And that structure works extremely well with the architecture that we employ.
Yeah, no, good point. And I think what you did is you focused on that kind of an architecture specifically to enable large amounts of ingest, right? You were thinking in terms of being able to serve use cases where you have very large amounts of ingest. Let's get it in as fast as possible and do what we can with it and not worry about having to get in there and change stuff later, right?
But by and large, I mean, the way I would equate it, it's like being, providing a motorcycle versus a four-door sedan. The motorcycle is going to have a more limited range of uses. You're not going to put 4 people and luggage on it. But if you want to get across town, efficiently and effectively, and you're one person and it's a heavy traffic environment, you're going to want the motorcycle. And again, for what we're talking about, our specific use case is storing and analyzing machine-generated data, which we think just absolutely aligns with the Internet of Things, because fundamentally the fuel for the Internet of Things is machine-generated data.
Okay, good. And we have a couple of specific questions here. One attendee is asking about how you compare yourself with some of the other tools that specifically talk about investigative analytics. I'm not sure if you're familiar with these. One is Palantir, one is Visual Analytics. Some of these obviously are more focused on the visual side. Would you complement a solution like that, or are those competitors?
Yeah, in most cases, we complement what the tool sets that most people associate with investigative analytics. So that would be, a range of BI tools, going from things like JasperSoft and Pentaho to the more the visualization tools like Tableau or ClickTech or Spotfire. And fundamentally, we will work with those tools. Different tools approach different tools approach memory management and how they organize the data once they pull it into the tool in different ways. And so there are, again, nuances to each. But we generally are fairly agnostic about the tools that work with us, and we are not trying to provide the BI layer on top. We are focused on the underlying database.
Sure. Okay. And speaking of technologies that you work with, what kind of hardware is optimal for what you're doing? You kind of mentioned memory use. Are there particular types of hardware, or you say you're agnostic, so commodity hardware, anything there?
Yeah, absolutely. I mean, we most of our customers are running on Dell or HP or just basically commodity hardware. And for that matter, from an operating standpoint, I would say 60 or 70% of our customers are on Linux, and then the balance are mostly on Windows. Okay,
good. And what about the knowledge grid? One of the attendees is asking, is the knowledge grid multidimensional?
Yeah. So dimensionality. So with a knowledge grid, fundamentally, it works best when you denormalize the data. So you can have fairly fat tables with many different dimensions. And that's really supported in terms of how the knowledge grid ingests and instantiates that data. So if you need to do dimensional analysis, it actually works extremely well.
Yeah, that's interesting. That's real interesting. Good. So what are some of the, you gave a bunch of different use cases, and to Robin's point, I think we're going to start seeing devices that take into consideration instrumentation in the future, or being able to pull data from these kinds of systems. Do you guys, do you spend any time talking to hardware manufacturers about what's coming down the pike? Or I guess the question is, what kind of research are you doing to see how you can align this technology even better for future use cases?
Yeah, that's a great question. We actually just did a little bit of reorganization because we need to. We have our own scale issues, which is certainly a good thing to have. But we have a research arm that is in Warsaw, and 3 of our 4 founders were associated with the University of Warsaw, which is sort of an epicenter for rough set math. And we are doing more and more research around how do we make the transition or the extension from what we're doing in the telco OSS space to what we believe the Internet of Things is going to require. So that's the imperative for our CTO and our chief scientist in Warsaw. We are doing things like joining the W3C, and I've had personally gone and had conversations there about what type of resources they bring to bear. So we are definitely looking at what we do today and how do we extend this on a broad basis into the Internet of Things. And I think that there's some pretty interesting things that will happen as a result of that. I'll just give you one example. We have a customer that uses us for analyzing all their IT resources on a global basis. It's a global bank. And, they have systems like OpenView and CapIQ and Splunk and a number of different systems that they incorporate to manage, to do log management. But what they found is that none of their systems scaled very effectively, and all of their systems only scaled at a very, very high cost. And what they were trying to do is figure out a way that they could gain a holistic view of everything that was going on and then use each system more effectively. And so they wrote a hub that basically absorbs messages from any log management system and standardizes it, and then they use a master repository, which is Infobright, and wrote basically a Java layer on top to perform the analytics against that. And sometimes they pass parameters back into the constituent system for doing further analysis. Like Splunk does, fantastic text manipulation and message management.
That's right.
And so it's a very symbiotic relationship, but they're leveraging the power of Infobright to gain that type of scale without deploying a team of people to have to manage it, on an ongoing basis or throw hardware at it to do it.
Yeah, see, that's a really interesting use case. Whenever you roll something out like that, if you would, feel free to share some thoughts with us about it, and we'll try to publish it at InsideAnalysis.com, because what you're talking about right there, it seems to me, is a very clever use of current technologies and new architectures, because I think the bottom line that I see in this whole disruption that we see happening in our industry is that you can explore really creative and new information architectures to handle all kinds of problems, but you do have to piece stuff together. You could go to one of the big guys like IBM or Oracle, for example, and I'm sure they could cobble together some of their tools, but if you can go best of breed and pull together a number of different tools, like you mentioned, Splunk, I can see what you guys have with Splunk being a very compelling use case of Gestalt, right, where the sum is greater than the sum is greater than the whole of its parts, right?
Right. Well, certainly the banks think so. The ones that are using us, cooperatively.
Yeah.
For sure.
That's very interesting. Yeah. Go ahead.
The one thing I would say is that ideally, it shouldn't be an issue. Of course, I'm talking about in sort of a Camelot-esque world. It shouldn't be an issue because as people go to the Internet of Things, they should think in terms of standardized messages. So if I have a mobile health message, if I have a connected city message, if I have a smart grid message, it's all going to be according to a standard message type, which there are certainly bodies at work that are pushing to do that. But that is not going to be how it's originally implemented. It's going to evolve in that direction. But along the way, there is going to be a need to also not only absorb this type of data, but in many cases, transform the data as you're absorbing it so that you can gain that holistic view of what's going on. And again, that's where we think that, the architecture means everything.
Right.
And there's a lot of smart people working on this. So I think that, I think the future looks bright. We just, again, we love being a part of it because it's really cool stuff.
Well, that is great stuff. Well, big thank you to both of our analysts today, and big thank you to Don from Infobright, and thanks to all of you out there for your questions. Those are some really, really good questions. They help keep us on our toes and keep us focused on where things are going in a very fast-moving industry. So thank you so much for your time today, folks. We really appreciate it. We will archive this webcast, as we do with all of them. Go to InsideAnalysis.com, look under Webcast. You can find the different shows that we have, the briefing room, of course. Hot Technologies is a new one, so we're glad that we could have our guests on today to help us define investigative analytics. I think it's something you'll be hearing a lot more about. So with that, we will bid you farewell, and thanks again, everybody, for your time and attention. We'll catch up to you next week. Until then, take care. Bye-bye.